Welcome back, guys. Today with binary analysis. This is the way Redstone can show numbers. We're going to be talking about three forms. First, we'll talk about normal round numbers, binary. Then I'll teach you about negative numbers. And lastly, we're going to be working with decimals. Let's get started. So, let's start with integers. Before we start with binary, let's look at our own way of describing numbers. Let's use Minecraft for this. So this is the number 314, of course. Everybody knows that. But if we take a closer look at how it works, you see that the rightmost digit is worth 4. One place to the left is worth 10, and one place to the left again is worth 300. Notice how the rightmost digit is worth 1, one place to the left again is worth 10, and then 100. Every place to the left multiplies the previous digit by 10. So we have 4 ones, 1 10, and 3 100s. Add that up and you get 314. Binary works almost the same, but instead of having digits from 0 to 9, binary only has the digits 0 and 1. So every place to the left multiplies the previous digit by 2 instead of 10. So you can start at 1. Then you have 2, then 4, then 8, etc. Here we have 1 0 0 1. The rightmost place is 1, and it is worth 1. Then one place to the left we have the 2's place with a 0. Then a 0 on the 4th place, and another 1 on the 8th place. So we have 1 1, 0 2's, 0 4's, and 1 8. Add those all up and you get 9. So 1 0 0 1 is 9 in decimal. Remember how we turned those 10 digits into 2? Well, let's try some other amount of digits, like 5 digits. We have the 1 place, 5 place, and the 25's place. We have a 3 on the 1's place, a 4 on the 5th place, and a 2 on the 25's place. So we have 3 1's, 4 5's, and 2 25's. Add those all up and you get 73. This is called base 5 because it's not 5 digits. The other number systems are called base 10, also called decimal, and base 2, also called binary.
But Tophead, is it really possible to make every single number with these systems?
Yes, Whitetap. Yes, it is.
And how do we make these numbers with redstone?
Well, great question. Let's say a 1 represents a signal being on, and a 0 represents a signal being off. So this number with lamps is 1010, or 10. One of these on/off signals is called a bit, and 8 bits together are called a byte. 1024 bytes is 1 kilobyte. 1024 kilobytes is 1 megabyte. 1024 megabytes is 1 gigabyte. A potato PC has around 8 gigabytes of RAM, so that means there are 8,589,934,592 bytes of RAM in your computer. And that means there are 68,719,476,736 bits of RAM in your computer. So that many ones or zeros. Isn't that insane? Now that you know how binary works, let me ask you something. Can you answer these questions? I'll reveal the answers after 5 seconds, and if you want, you can pause. So, these are the answers. Tell me how many you got right in the comments.
Very cool stuff and all, but Tophead, how do we make negative numbers?
Well, we have 2 types of number systems. One is a bit harder than the other. Let's talk about the first one, which doesn't really have a name. So, we have our binary number here, and we have this 1 bit up front. This bit is called the sign bit. When it's on, it means the number is negative. It's that simple. So 11001 is minus 9. Yep, it's that easy. Now the complicated method. This one is called 2's complement. The first bit is the sign bit again, but when you want to make the number negative, you have to flip all the bits. So 1's become 0's and 0's become 1's. And you also have to add 1. So let's try to make negative 9. So let's start with 9. 0, 1, 0, 0, 1. We flip all the bits. 1, 0, 1, 1, 0. And we add 1. So it's a bit complicated to do it right now. So this is an easier way. We flip only the rightmost bit. And if it was on, we flip a bit to the left as well. When it was on, we flip the next bit to the left as well. All the way until you get a bit that was 0. Now let's try this with the 1, 0, 1, 1, 0. So we add 1, 1, 0, 1, 1, 0. We flip the rightmost bit, 1, 0, 1, 1, 1. And it was a 0, so you don't have to do anything else.
But Tophead, why does this way even exist?
Well, little voice in my head, it's quite simple actually. It's the way to do subtraction. If you make a binary adder, we'll do that later, and we put in a negative number in this way, it will do subtraction. Now that you know how this works, can you answer these questions on the screen? You can pause if you want. These are the answers. Tell me how much you got correct in the comments. Now, let's talk about decimals. Let's look at the way we do it in decimal again. So here we have the number 9.25. We know that every place we go to the left multiplies by 10. Notice how every place to the right also divides by 10. So here we have a decimal point. It shows where the place is that is worth 1. So let's say we go behind that decimal point. This would be worth 1/10. Then this one would be worth 100. So it divides by 10. Let's go back to binary and see what will happen here. Let's first add the decimal point, so we know where the ones place is. So this is the ones place. So one place to the right is the halves place, then the quarters place, and then the 1/8 place. Let's try to make 9.25 in binary. So we have a 9, that's 1, 0, 0, 1. And then we have a quarter. So the 1/4 place needs to be on. So the answer will be 1001.01 in binary. This is called a fixed point because the decimal point is fixed in place. Now that you know how this works, can you try to answer these questions? I'll reveal the answers in 5 seconds again. Here are the answers. Tell me how you did. But how do we make numbers like 0.4 in binary? Well, it's actually impossible. It's the same issue as that you can't make numbers like 1/3 in decimal. People thought of a solution and they found one, but it's so complicated that redstoners don't use them. Only real life computers do. If you're interested in some computer science, then stay. But if you think your brain is gonna explode, I would recommend just skipping to this time on the screen. But good luck understanding me if you didn't click off. I'll try my best to explain how this works to you guys. Okay, so some floating point numbers are 32-bit, so they have 32 bits. The first bit is for the sign, so when it is on, the number is negative. Then comes 8 bits for the exponent. And the last 23 bits are for the mantissa. First, let's talk about the mantissa. It's basically a number that has 4 bits for the integer part and the rest is for decimals. So the first bit is 8, then 4, 2, 1, 0.5, 0.25, etc. So what happens is the mantissa will be multiplied by 10 raised to the exponent. It's basically scientific notation. But for scientific notation, we also need negative numbers for the exponent. So, there will be 127 subtracted from the exponent. So, when we have 255, it will become 127. And when we have 0, it becomes negative 127. Now let's try to fix that problem from earlier. We can make 0.4 by putting 4 as the mantissa, and then we put 126 as the exponent. The exponent becomes minus 1 then. So then it does 4 times 10 to the power of minus 1, which is 0.4. But this isn't used by simple laptops, only by things like banking, which needs lots of precision. Why? Because raising things to the 10th power is hard. I'll explain why later. Normally, the mantissa only goes from 1.0 to 1.99999. Well, as many 9s as possible. This isn't completely true, as it actually just goes from 0 to 0.99999. But it adds 1 later. So when we have 0.25, it adds 1, and then 1.25 is our mantissa. And then it does the mantissa times 2 to the power of the exponent. This is easier because notice how shifting bits to the left or right multiplies by 2 or divides by 2 in binary, just like it multiplies by 10 or divides by 10 in decimal.
But Top Hat, this still doesn't fix the 0.4 problem.
Yes, that's true, but modern computers don't care. That's why sometimes when you do 0.2 plus 0.1 in a computer program, it outputs 0.300000000000004 because it doesn't have enough bits to make it perfectly precise. But what does it solve then? Well, with fixed point, you lose room to bits that give you decimal places. But in floating point, you can sacrifice integer precision for decimal precision, and vice versa. Look at this. In fixed point, with 32 bits, you can only make numbers to 65,535. This may sound like a lot, but without the decimal points, you can go to 4,294,967,295. But with floating point, you can sacrifice a lot of precision on the decimal part and still go to such high numbers. Or you can make really small numbers and then you can have a lot of precision on the decimal part. You can basically move the point around. This is where the name floating point comes from, because the point is able to go anywhere. This is also where the name float comes from in programming, because you can use a float to have numbers with decimals. So guys, tell me, did you get all of this? The most important part is to know how round numbers work. So don't worry if you didn't get the rest, because I'll explain them a second time once we start using them. It's a good idea to remember the numbers from 0 to 15. Here's a list of them. So next episode, we're gonna talk about logic gates. These things are needed everywhere in Redstone. We also need them to make addition. These things are really simple, so don't worry about your brain exploding like in this episode. Thanks for watching, and I'll see you in the next episode. Bye!